being the first talk in the morning. I hope that you have a good coffee. So, my talk is about the emission concept that my co-authors and I have been developing in the last year. And as you see from the presentation, it might still look rather preliminary. But we are trying to work hard on developing the concept, and we will definitely appreciate your inputs. It targets the planet Mars, its atmosphere, and its weather. What we want to do is to put a Mars stationary satellite in orbit, where a Mars stationary orbit is basically an equatorial, circular, and planet-synchronous orbit. Okay? It's also called aerostationary, because you know Mars is Ares in Latin. So in plain words, what we want to do is to look at the same spot on Mars all the time and monitor the evolution of the dust and water ice clouds. And here I have an example of such a dust clouds on Mars. So having set the scene, let me now make the case for such a mission concept, starting from a scientific question, which is, what are the processes controlling the dynamics of the atmospheric circulation on Mars and promoting the evolution of the regional storms into planet and circling storms, which are storms that are covering the whole planet. This is one of the main scientific questions on Mars, and this is what we would like to answer with a novel mission, a novel way to look at things on Mars. So, just to give you a very brief summary of the importance of dust and water ice clouds on Mars, we know that both aerosols affect the weather. They have impacts on the thermodynamics and the dynamics. Weather, what we mean by weather is basically winds and circulation, okay? Dust storms and clouds, all this is weather. We need to monitor the weather continuously because mainly we want to improve weather forecasting on Mars. And why do we want to do that? Because we are sending robotic missions, and in future, hopefully, we're going to send humans there, and we want to know where a dust storm is passing over your head. It's better to know. Now, a Mars stationary orbit is ideal for several reasons. It allows to monitor the evolution of these aerosols, and you also can monitor quite well the evolution, the changes in surface properties, such as the albedo, for example, after a big regional storm. So when the storm cleans or deposits dust in an area, then the albedo changes, and you can monitor that. Why a Mars stationary orbit is interesting? That's because you can see, you can look at a very large region, fixed region, the same spot all the time, or more or less. You can look beyond 60 degrees from the sub-spacecraft point. Practically speaking, you have at least 60 degrees out of the sub-spacecraft point to monitor all this stuff. You can follow the dynamics at all local times throughout the seasons, and obviously you can have a very high sampling rate. So, in my opinion, is the best way to look at the evolution, the temporal and spatial evolution of dust and water ice clouds. I'll give you an example because it's better to look at things rather than talking about things. On the left-hand side, you have Mars in a visible image taken by an instrument on board Mars Global Survey, which is a spacecraft now not active on Mars anymore. On the right-hand side, you have a UV image taken by a spacecraft which is taking measurements right now and looking at the upper atmosphere of Mars, Malin. What you see, or what you can't see actually, on the left, you're supposed to see a dust storm going on at that time. It's not very clear, but don't worry. In a second, I will show you something that makes it clearer. On the right, you definitely see some very nice water ice clouds forming at the top of the volcanoes. Okay, you also, if you saw the image clearly, you will see some storms as well. Now, I told you about this image, not very clear, right? But what about that? So that is basically the same day, but instead of looking in the visible, we are now looking in thermal infrared. In particular, here we are seeing the column dust opacity retrieved from the thermal image. Okay. Now the problem is this looks very nice, sure, but it actually is a reconstruction from real data taken by this spacecraft, and the real data actually looks like that. Okay. So the Mars Global Surveyor was a polar orbiter, and it looked at the same local time, except for the polar regions, obviously. And in reality, what you have dwarfs like this. And you have 12 of them each day. Yes, you can reconstruct the entire disk, but in reality, what you really have is this kind of stuff. And if you look at the evolution of this kind of stuff, so this is the storm I was showing before. So you are now going through different days or sols on Mars, in that particular Martian year. So, you're basically looking at the evolution of this regional storm. Not very clear to me if you're looking that way. It's much more clearer if you look in this way. Again, this is reconstruction from those data. A few more details of how we reconstruct the evolution of this storm. You can look at this paper. But basically, what I'm suggesting is that if we look at Mars in an aerostationary orbit, and this is actually projected as if you were seeing from an aerostationary orbit at more or less 17,000 kilometers above the equator, then you will be able to see the evolution of such storms, as well as water ice clouds and formation, evolution, and decay, and dissipation of dust clouds. Because all these phenomena have a short time scale, so you have to follow them continuously. Okay? So that's my reason for this mission. Now, from a technical point of view, what we are proposing is to send a 12U CubeSat, which has a mass more or less of 24 kilograms, taking into account 24% of margin. Obviously, after yesterday's last talk, I'm wondering whether it's actually a CubeSat they want to send to Mars or rather a SAB nanosatellite. Well, it's debatable. Anyway, it's also it's clear to me that it's not a cube. It's more like a not a cube for sure, because it's 3 by 2 by 2. But it's a satellite for sure, and uses solar electric propulsion. So we are proposing to use ExoTerra, which produces this bus called Halo. It's a Hall effect micro thrusters based on solid iodine propellant. So the idea is to have a 2.6 kilogram solid propellant, and the solar power will be produced by a rolled, at the beginning will be rolled boom of solar rays, which has a power at the end of life at Mars of 186 volts. That's enough for the type of science we want to do. We're thinking about providing 50 volts for science operations during daytime and 18 watts during eclipse time. Because the advantage of this is that we're looking through the day and through the night, and that will allow us to follow the evolution of this meteorological phenomenon throughout the local times. This Halo is still a prototype, but they're going to fly it in 2019. There's a test planned, and the solar array has been developed through a NASA grant. So the advancement of the spacecraft is quite a good stage. We are planning to use an iris communication system, patch antenna, and all the other details I can talk to you later. But basically, it's kind of standard CubeSat except for the propulsion systems and possibly for the big solar arrays. What I consider quite innovative is the mission design and the particular trajectory that we're going to use. Because we want to put it in an aerostationary orbit. It hasn't been done before, as far as I know. So the journey to Mars, right now, it will be ride-sharing on a mothership. We'll be attached to an orbiter because we want the orbiter to perform the orbit capture for us before being deployed. So our CubeSat will be deployed around 310,000 kilometers far from Mars, and then we'll be spiraling down to about 20,000 kilometers, which is from the center of Mars, which is the aerostationary altitude. We're going to use a total delta V of 1.22 kilometers per second. We'll be having a good margin. We'll be having quite enough delta V for all the operations in aerostation orbit. And the duration of the mission is going to be 1 Martian year, plus possible extension. What about the payload? Well, certainly we want to put a visible camera because it's cheap, it's ready to go. There are off-the-shelf camera, which are very light, which are very small, and we can have a 4.5 kilometer resolution, so it's good to look at regional source. Probably not a local source, but a regional source are okay. But what we really want to put is a thermal infrared camera, because as I showed you, if we combine visible and infrared, we can get a product which gives us a continuous data day and night, and we can really follow the dynamics of the dust and clouds all the way through the solar cycle. We want a camera that has at least a resolution of 15 kilometers per year, and we wanted to cover a quite wide range between 7 and 16 micron, because we would like to have 3 channels for the CO2, 3 channels to retrieve the temperature from the CO2 band, 1 for the surface temperature, 1 to retrieve dust opacity, and 1 for water ice opacity, and then 1 in between, which is useful for retrievals. Optionally, a UV camera would be nice, but then you have to really trade off weight and space. The final products then would be images for sure, with high sample rate, about 30 minutes, which is a good scale for evolution of water ice and dust as well. But not only images, we want retrievals, we want quantitative data. And I think we can do it. We can retrieve temperature and aerosol optical depths, dust and water ice, and then we will have 2D maps of these optical depths and 3D maps of temperature. Although for temperature, we can't do the best. It's still a small satellite. So the idea is to have at least 3 independent points, 3 vertical levels. So we have 3 measurements of temperature between, let's say, 5 and 45 kilometer altitudes, which is still quite good. And it could be used for doing data simulation, doing a lot of stuff to reconstruct not only the dynamics of the aerosol, but also the winds and temperature structure in the winds. Data downlink is a challenge. We'll need to trade a few things. Maybe thinking about onboard storage and pre-processing. And we would like this product to be available straight away for everybody, even for the public. So, what do we need now? First, funding. Everybody needs funding. Yes, we do funding. We do need funding to develop the mission concept further. But also, we need collaborations. We need to talk to you guys because there are challenges. The payload is a challenge. We need a thermal infrared camera or an equivalent imager. multispectral imager, which is more, and we need to talk to you about delta V if you know, if you have ideas, because what we want to do is to increase the number of mission opportunities. We would like to, for example, being able to do orbit capture by our own instead of relying on a Martian. We need to solve the communication problem because so far we are using Iris module, which relies on communicating through a relay satellite. Okay? We would like to be autonomous, maybe using JPL captor, high gain antenna. The weight and mass is okay. We need to do some pre-processing because we cannot downlink all the data in a very high frequency rate. So maybe using techniques based on neural networks, citizen science networks. If you guys have experience or ideas, please come and talk to me. The pointing is a challenge as well, so we need to discuss that as well. And then obviously, what we really need is an opportunity for launching this after having developed the concept. We need an opportunity to launch this first aerostationary satellite. And I think with that, I will thank you for your attention and feedback. Thank you, Luca. My name is interesting. Do we have any questions?
Very interesting talk. I'm wondering, the power, all of those solar arrays that you have, is needed for the payload or for communication purposes? Because as far as I can understand, it's also needed to feed the electric thruster. But I'm wondering if you are sizing the solar arrays only for the transfer phase or for the operation phase?
No, for both. Actually, science is not eating a lot of power. Thrusters are eating 150 watts when they are used. We're not using them all the time, it's true. You might just need it to adjust the trajectory to station keeping thermally. But communication, yes, communication is one of our big eater because the idea is to have a high frequency sampling rate. Therefore, we have to, in principle, we need to downlink quite often.
Because solar electric propulsion is efficient whenever you have a high power payload. Because since you have to feed the payload, then you use the power that you produce also for the cruise. So I was wondering if the things are balanced here or if the sizing case for the solar arrays is the thruster.
I think the thruster are quite important because especially when you want to spiral down to get to this stationary orbit. The thrusters will be on all the time.
Have you considered using an alternative technology for propulsion? Propulsion?
Well, what we want to avoid is using chemicals that can be a problem for security to the main payload. So the idea of using a solid iodine propellant came to avoid all the problems with the launch and explosions and chemicals and stuff like that. So, in principle, we would like to avoid that if we can. But if you have any other propulsion system to suggest, why not?
So,
sure.
So I realize in a short period of time you probably don't have enough time to present all the trades that you've done, but I've looked at a similar concept, and aside from all the minor miracles that are needed in terms of new propulsion and solar and all this other stuff, the COM is really the absolute limitation, and it severely, if not completely, restricts the number of images that you can send back, even with very aggressive compression and other techniques. I mean, the problem is your orbiter is looking down on all the other orbiters that can serve as relay, and their antennas are pointed in the wrong direction. And even with the most current getting antennas that you can get taking up some reasonable area of your CubeSat, you can't send all that data back. And furthermore, the cost of DSM looking at you for the amount of time it would take to send it back is exorbitant. So what's the solution?
I don't think I have a magic solution. I have ideas that have to be developed further. Let's say that you're absolutely right. We cannot send images at high frequency all the time. There's no way. But what we can do, we don't have dust storms all the time. We don't have water ice clouds all the time. So we should take advantage of that. We might need to take images all the time, but we don't need to transfer them all the time. We can keep that on board for a while, and then maybe transfer only a low resolution image, check whether there is an interesting phenomena going on, and then at that time say to the spacecraft, okay, great, now the images that you're buffering, transfer them. We might need to focus on specific, very short time campaigns rather than just looking at Mars all the time. I think we need to trade off with that.
The constant monitoring of atmospheres is very important topic. And are you considering also other planets, or is this much far?
I think Mars is already a lot of time. By now, I am focusing on Mars, and I'll be close to finish my career. Some other plan. I think right now I'm really focusing on Mars.
So in answer to the earlier question about how do you get the data back, if you look forward 30 years, let's say it's 30 years, and there are humans there, the answer's obvious. The data goes straight to a ground station at Mars. So why not think about architectures that use landed assets that have finished their science mission, for example?
Okay, I have another question. I was wondering how you are going to do the attitude control. Because I think that the purpose you are having with your satellite, you really need to have extremely accurate control. And on Mars, you don't have a magnetic field, like on the Earth, for example.
Yeah, we use a blue Canyon attitude control system for that, and then we have some microprocessors to control the attitude, and basically they are able to have a good attitude control even without the magnetic field. I think on the top of my head, we're talking about like 0.007 dB, less than that. Control. Maybe it's average. I'm not an expert on that, but I think it's a good one. The problem is, as you see, we don't know the impact of the big solar rays on that. That